One of Taylor identities for on-shell green functions, which are the building blocks of S-matrix elements. And let us apply what we did in the morning to Slavnov-Taylor identities. So we do exactly what I already outlined. We begin with a Slavnov-Taylor identity. This is a generic Slavnov-Taylor identity with this abbreviated notation, where the notation means that we apply all the BRS transformations of all the individual fields, and after doing it, we amputate the external legs and go on shell. So we apply this algorithm of multiplying with the inverse external propagators and then performing the limit of on-shell external momenta. So how do the resulting terms look like? So one term would, for example, be phi 1, and then here there is one BRS transformation of one of the field operators in the middle, and we go on shell and amputate. Now, how do the BRST transformations actually look like? There are two different ways how they can look like, or there are two different kinds of terms in the BRST transformations, and we now must distinguish between the two kinds of terms. We already stressed a few times the differences. Namely, one possibility is the result is linear, and by linear I mean linear in all the quantum field operators of the theory. Small check, who remembers a term in a BRS transformation which is linear in the quantum fields? What, for example, would be the term which is linear on the right hand side? The derivative d mu c. And actually, for non-abelian theories, that your example is the best example, because the BRST transformation is the covariant derivative of the ghost, and that contains a normal derivative of the ghost, but it also contains a term proportional to a mu times c. Now that is linear in the quantum fields. That is a quantum field. So this is linear in quantum fields, but that is not linear, but bilinear in the quantum fields of the theory. So this is a term which is linear, and on the other hand there are non-linear terms, and your example shows how both kinds of terms look like. For example, let's briefly, so that is the BRS transformation of C. What is the BRS transformation of a quark field, for example? How does it look like? It's an infinitesimal gauge transformation of a quark, where the gauge transformation parameter is replaced by a Fadeev-Popov ghost. So you have minus I times gauge coupling times C times the quark field. So that, is it linear or non-linear? It's non-linear, right? So it contains ghost times a quark field. So that has no linear term. That has one linear and one non-linear term. Okay, so let us now go on. How do Feynman diagrams look like which result from the linear terms? Such Feynman diagrams look like follows. So a linear term S of phi L would be something, let's say, proportional to some yet another field phi k, but only one phi k. So then what stands here is a green function phi 1, phi 2, and so on, and then phi k, and so on up to phi n. So that is just an ordinary green function with an external field phi k. Therefore, it looks like this. Here we have phi k, then it goes on in the normal way. Then we have all kinds of Feynman diagrams, and then we have all the other fields. Okay. So this is an ordinary green function with lots of external fields. What, however, happens in the nonlinear case, so for example here, let's say we have phi k times phi j as an example, product of two field operators, then we have here an expectation value of a product of elementary fields, and here we have a product of two fields at the same space-time point. So that actually is similar to what you have if you derive Feynman rules. If you derive Feynman rules, then you know that here you have I times integral over an interaction Lagrangian. The interaction Lagrangian contains many products of fields at the same space-time points. And what are the Feynman rules for those terms out of L int? They correspond to vertices, where several lines go to the same space-time point. And that is exactly the same case here. So here we will have now at an external point, we have a vertex where two lines end. One line corresponds to phi k, one line corresponds to phi j. That is the external point of the Feynman diagrams, which is the counterpart of that external point over there. And then you have all Feynman diagrams, and otherwise you have ordinary external fields phi 1 up to phi n. But this special point is an external point onto which directly two lines must be attached. Whereas here you have an external point with one line attached. Now, what does that mean in momentum space? In momentum space you do Fourier transformation, then at each external point there is now a momentum inflowing. So here you have external momentum PL inflowing, PL, here momentum P1 flows in, and so on. And here also overall the momentum PL flows into the diagram. And remember, we want to amputate the external legs and go on shell. That means we multiply with the inverse of the external propagators. That means in particular we multiply with the PL square minus M square. We multiply with PL square minus M square. And then we set PL square equal to M square afterwards. That means we get a non-zero contribution if the Feynman diagram to begin with contained 1 over PL square minus M square. This is an ordinary line which has an ordinary Feynman rule for a line. It might contain 1 over PL square minus M square. So this might contain a pole. Like 1 over PL square minus M square. However, here that is not possible. This cannot contain a pole because the momentum PL is immediately distributed into the two lines. So for example, we get one line PL minus K, and here we just get the momentum K at the other line. And K might either be a loop momentum which is integrated over, or it is some other momentum. Anyway, there is nothing which contains a pole 1 over PL square. PL square doesn't exist. So therefore this cannot contain a pole. So therefore, there is something important which happens if we go on shell and amputate the external legs. Namely, the terms resulting from nonlinear expressions in the BRST transformations, they completely drop out. That is the dramatic simplification I announced.
طبعا هنا في موضوع مهم جدا جدا، وهو كان ذكرته في كتاب الحلقة 55 أن الجوست اللي هو السي جوست يعبر عن ملتي انتراكشن أو ملتي، نقول ملتي فيلد، لأنه هو عبارة عن كومبينيشن. الآن هذا المحاضر يلف حول هذا الموضوع بما أدخله بال اس بي ار اللي هو الأوبريتور بي ار اس تي. الأوبريتور بي ار سي عبارة عن ماذا؟ عبارة عن يعطيك يعطي field of ghost. يعني هنا إذا اشتغل هنا عندما طبق الأوبريتور اس بي ار اس تي أعطى جوست، وأصبحت المعادلة بالنسبة للأي ميو أصبحت بايلينير ولينير، لينير في الديريفيتيف وبايلينير في الحد الثاني. وفي المعادلة الكوارك أصبحت بايلينير مباشرة، اللي هو في 2 فيلد بتاع الجوست وفيلد للكوارك. هذا ما كنت أريد أن أقصده في الكتاب السابق، وربما يكون يعني لم أوضح الرؤية كما تجب، لكن القارئ سيفهم ما أقصده إذا شاهد هذه المحاضرات. فهذه يعتبر طاقة إضافية أضيفت في التفاعل، وهذا يفعل آلية قوية للفضاء صناعي الأبعاد، بحيث أنه يطرد مزيدا من الكتل. لهذا يمكن، أنا ذكرت أنه دراسة اليانغ ميل بهذه النظرة يمكن أن تخبرنا بزيادة الطاقة، ماذا تؤدي، كيف تؤدي زيادة الطاقة في التفاعل إلى خروج المزيد من الجسيمات من التفاعل بهذه الآلية. وبالتالي يمكن أن ندرس شيء في غاية الغرابة، وهي أنها يمكن أن يكون لها تطبيقات. يعني ممكن أنه كما يقال أنه هناك ليزر عالي الطاقة بحيث أنه يفجر الفراغ. كيف الليزر عالي الطاقة يفجر الفراغ؟ بهذه الآلية. يعني الليزر الذي زاد عن طاقة معينة فإنه يفجر الفراغ ذات نفسه. كيف يفجر الفراغ؟ لأنه هذا الليزر يتصادم عند مستويات دنيا، مستويات صغيرة جدا جدا. هذه المستويات الصغيرة ليزر عالي الطاقة عن طريق اليانغ ميل ايكويشن والصياغة البي ار سي. هذه الصياغة تعطينا جوست فوتون أو جوست بارتكلز. هذه الجوست بارتكلز عبارة عن كومبينيشن، هذه الكومبينيشنز في الفوتونات الجاية من الليزر. هذه الكومبينيشنز تعطي للفضاء صناعي الأبعاد طاقة إضافية مركزة في التفاعل في مساحة أو في حجم صغير جدا، مما يفعل الفضاء صناعي الأبعاد قوة أكبر لطرد الكتل. بالتالي هذا ما يسمى تفجير الفراغ، ولكن هو في الحقيقة الفراغ لا يتفجر، وإنما هي آلية من آليات الفضاء صناعي تفعيل آلية الدفاع النفسي. إذا كتاب المعلومات التي قدمتها في كتابي هي صحيحة، لكن يعني تحتاج صياغة أكثر حرفة وأكثر دراية، لكن هي صحيحة عموما. وهذا ما يجعلنا أن نبحث عن تجارب لهذا الموضوع، ونبحث في الإنترنت عن إذا زدنا الطاقة ماذا يحدث. طبعا ستخرج جسيمات أكثر، هذا معروف، لكن هل هناك مختبر في العالم استطاع أن يخرج جسيمات بحيث أن خرجت بطريقة انفجارية؟ طبعا هذه الطريقة ستعطينا معلومات أكثر دقة وأكثر عن هذا العالم الغريب الذي يسمى بالفضاء صناعي الأبعاد، الذي يستطيع أن يدافع عن نفسه وينتصر في النهاية. تعطينا معلومات عن هذا الفضاء الغريب جدا.
Most BRST transformations are nonlinear. They all drop out. The only thing that does not drop out is the linear part of BRST transformations, like for example this term. Everything else will drop out if we amputate and go on shell. So in this, amputate on shell, only linear terms in S phi I can contribute. And that is a big simplification. And just to note it and to not forget about it, let us write down the complete list of all linear BRST transformations. Here is already one, but let's be complete. So the linearized version is linearized of A mu is d mu Ca. And the nonlinear part drops out. So then the linearized BRST transformation of a gluon field is abelian. The non-abelian part drops out and it looks like the abelian BRST transformation of a photon field. What other linear BRST transformations are non-zero? For example, quark BRST transformations become zero. What else is non-zero? Right, S linearized on C bar gives B, that is linear, and S of B is zero. Anything else? What is the BRS transformation of a ghost? Yeah, so that is also non-linear. So that's all. That's all. That is the only non-linear, only linear BRST transformation. As rest is all zero. So that is a dramatic simplification. Almost everything is now zero. By the way, this changes in Higgs theory. If you have spontaneously broken gauge theory, then there are some additional linear parts of the BRST transformations which have to do with the Goldstone bosons and the masses of gauge bosons. And as you know, I hope you know, what does it mean if something is BRST invariant? It has the chance of being something physical. So the BRST invariant stuff, like for example the quarks, they are physical fields. And also the BRST invariant parts of the A, which are not BRST transformations of something else, they are also physical. Now physical, unphysical degrees of freedom in a Higgs theory change, because there the gauge boson has 3 physical degrees of freedom instead of 2 because of its mass. And some Higgs degree of freedom, namely the Goldstone degrees of freedom, they become unphysical. And therefore this structure here must change. And indeed it changes. And so if you look at the linearized BRST transformations in a theory with Higgs mechanism, then there are some additional non-zero terms, which means some additional Higgs fields become unphysical, and vice versa. Yep. But it appears as the BRS transformation of something else. So it's also unphysical. Right, but it is on the linear level, it is BRS invariant. But it's the BRS transformation of the photon, namely, precisely speaking, the longitudinal part of the photon transforms into the ghost. So it's part of this BRST quartet. Okay, very good result, and that is what we can now apply. So I think that is, if I remember correctly, this is the last section of this chapter. I wanted to give you some examples and a sketch of the unitarity proof. Yeah, it's a little bit up to you how many examples we want to do. For sure, I want to do the example which also is on the exercise sheet, namely for this mu-nu relation to M for the glue-glue final state versus ghost-anti-ghost final state. That is one example which is obviously important for the unitarity of the S matrix, and I would like to derive the general Slavnov-Taylor identity from that procedure. But we can also do another simpler example which connects to the Lorentz invariance discussion from before that we had. So yeah, I see you are already a little bit tired. And how much energy do you still want to invest into the lecture? Can you confirm that then we will still do something in the exercise? The point is that is not for the video, but next week there is holiday, right? So therefore it's nice to do this completely, and then in 2 weeks from now we will start something new. But then today we will discuss everything that needs to be discussed on this topic. Okay, so one example for, and by the way, you can also view everything I say here and now as part of the exercise, because it really could also be an exercise. But I will do it. So let us derive something for this green function. So remember 2 weeks ago, or some weeks ago anyway, we discussed this as one of those typical miraculous problems with miraculous solutions, because if you calculate it, then you have here a psi dependence of the propagator. And the question is, does the psi gauge parameter drop out if you calculate the full S matrix element? And somehow it did drop out. How did it drop out? Who remembers it? It drops out because the psi dependence appears. Is it possible that some of you explain how the psi drops out? Somebody able to explain this? No? Okay, so what is it's like an exam question. So the answer could be the propagator depends on psi, but the psi dependence is only in the longitudinal parts of the propagator. Psi multiplies p mu in the propagator. So then that p mu term hits this line here. And then the question is, what happens if you contract the entire line with the longitudinal photon momentum p mu? And there is a Watt identity or Slavnov-Taylor identity which tells us that if you contract the entire fermion line with the photon momentum p mu, you get 0. And that somehow corresponded to current conservation. If you regard the entire line as a current, J mu, then you get in momentum space P mu times J mu equals 0, corresponding to the total derivative d mu J mu equals 0 in position space. So current conservation, or the fact that longitudinal momentum contracted with a current gives 0, that is the origin of the independence of psi. Let us derive this from a Slavnov-Taylor identity. Okay, so this same relationship, that the contraction of the line with p mu gives 0, that is a Slavnov-Taylor identity. Previously I called it Watt identity in the QED case, but for QCD I call it Slavnov-Taylor identity. So let us derive this. So what do we need to do? We use this. this identity C bar psi psi bar and take the BRST transformation of it and set it to 0. That is a Slavnov-Taylor identity. Okay, so what happens? We get one term where we have the BRST transformation of the anti-ghost times psi psi bar plus a term minus, because of Fermi statistics, C bar times BRS of psi times psi bar plus again C bar psi, the BRS of psi bar. Okay, and so the sum of these combinations is 0. Now we can look at the terms. Let's say this is term 1, term 2, term 3, and let us do it in momentum space. In momentum space, let us assign some incoming momenta into all those field operators. Then which momenta should we assign? Let's say we assign the following incoming momenta, minus q, then p and minus p prime into these field operators. And then this is true for all the 3 green functions, because of course we do a uniform Fourier transformation of the entire equation. So here, here and here the same momenta must be incoming. Good, then let us discuss what this means. So for example, what is actually, maybe let's start with the second. What is the result of the second green function at tree level? What is the tree-level Feynman diagram corresponding to this green function? So in order to get the Feynman diagram, of course, you need to know what is the BRST transformation of psi. And you know it because I just wrote it down a minute ago. This is minus I times gauge coupling times C times psi, so it is nonlinear. Therefore, we need Feynman diagrams which are not ordinary green functions, but which correspond to diagrams where we have one special vertex, a 2-point vertex, where at one space-time point there is a line attached for a ghost and a psi. Let's use this simple square for such special vertices corresponding to BRS transformations. Then we have here this vertex, and attached to that vertex is an incoming ghost line and an incoming fermion line. Because at this point there is a field operator C and a field operator psi. And in the mathematical expression that would be multiplied with minus I times gauge coupling. And also I neglect here the gauge group indices A, B and so on, because they are not important for this calculation. Okay, so that corresponds to this vertex, and then we need otherwise an external C bar. So there must be an external point with a C bar, and there must be an external point with a psi bar. How can a Feynman diagram look like which contains this vertex, this external point and that external point? For example, like this. Now we have a Feynman diagram with an external C bar, an external psi bar, and a special vertex where C and psi are connected. And so this would be a Wick contraction between C and C bar, which is the ghost propagator. And here we have a Wick contraction between psi bar and psi, which is the normal Dirac propagator. What is the value of this Feynman diagram in momentum space? The value, let's first write down the value of the special vertex minus I times G. And then in momentum space, we have here the rule for the ghost, which is I divided by the ghost momentum. What is the ghost momentum? So here into C bar, into, what is it? we are here. So into C bar there flows the momentum minus Q. So on this line we have Q. Therefore the ghost propagator is I over Q square. Then into psi bar there flows minus P slash. So on this line in this direction we have plus, P prime. And then this line is I divided by P slash prime minus M, where M is the fermion mass. That's the value of this Feynman diagram. And the third Feynman diagram is similar. There you exchange the role of psi and psi bar, but it looks similar. But the fermion line goes into the opposite direction. What, however, is the result of the first term? The first term here has B, but B is now equal to minus 1 over psi d mu a mu by using the equations of motion. Therefore, here we have a linear BRST transformation, and therefore this is an ordinary green function. An ordinary green function, but multiplied with 1 over psi and with a derivative in momentum space that is simply a product with a momentum. But otherwise it's a normal green function. A normal green function with an external A, mu, an external psi, and an external psi bar. Now, how can a green function with a normal A mu, psi and psi bar look like? Feynman diagram, for example, this one. With an ordinary vertex here for Yang-Mills theory, gauge boson, fermion, anti-fermion vertex. It's a green function, not one particle irreducible, but a full green function. Therefore, the three external propagators are part of the green function. So what is the result of that green function? The result is, and by the way, so 1 equal, so 1 contains minus 1 over psi, minus 1 over psi, times the momentum, and which momentum? So d mu becomes minus I times the incoming momentum. So in this case, d mu becomes plus I q mu times I q mu. So we have minus I q mu divided by xi. And then we have the Feynman rule for this green function. So what is the Feynman rule for this green function? It is first of all the gauge boson propagator, which contains minus I over q square, then times the complicated thing, g mu nu minus q nu divided by q square times 1 minus gauge parameter psi. Let's use the gauge parameter here for fun. Then we have the vertex. Then we have to go along the fermion arrow. So let's begin here. So then we have the incoming momentum here into psi is p. Therefore we have here p going in that direction, and here we have p prime into the other direction. Therefore we have I divided by p slash minus m times the vertex minus I g gamma nu, then I divided by p slash prime minus m. All right. Now, what happens if we amputate the external legs and go on shell? So I give you 20 seconds to think about it. What happens with this Feynman diagram if you amputate the 3 external legs and go on shell? Or should we first do the last line? If you remember what we discussed half an hour ago, you should see and know, even without calculation, what happens. What did I tell you half an hour ago? The conclusion of the previous blackboard. What would that mean for the diagram number 2? But is that a linear or a nonlinear BRST transformation? Diagram 2. Right, it should go to 0, right? Shouldn't it? Actually, it should go to 0, because that's what we stressed. Didn't we stress it? We stressed it, right? We stressed that only the linear BRST transformation survive. We derived it actually in general. Now, what happens if we go from the general to the concrete case? It should still remain true. What does it mean? You multiply with the 3 inverse propagators. Which 3 inverse propagators? For the 3 external lines. But there are not 3 external lines. Why not? Because of the nonlinear BRST transformation. The 3rd external line is missing. It doesn't exist. It doesn't exist because of that. This point here is that. And here you see exactly what I told you in general. You should have an external momentum PL. In this case, you should have an external momentum for psi, which is called P. There should be an external momentum P. But there is no line which carries the momentum P, because at the external point the P is immediately distributed into 2 lines. One line with Q and one line with P prime. The sum of Q plus P is P. Q plus P prime. So P is distributed over 2 lines. But there is no single line which carries P, and therefore the diagram does not have a pole 1 over P square minus M square. Therefore, if we amputate, in other words, if we multiply with the 3 inverse propagators, we also multiply with P square minus M square, and then we set P square 2M square, and then we get 0. That is the point. So we get 0. So we get 0 because of P square minus M square goes to 0. And in the 3rd diagram it's vice versa, so P prime square wouldn't exist there. So, but that is exactly the example of the general case. So it's as simple as that. So we amputate all 3 external propagators for all 3 fields. And here there are just not 3 fields. That's the point. So the general statement is true here, and it means that 2 out of the 3 diagrams completely vanish. That is nice. So what about the 3rd diagram? The 3rd diagram is an ordinary green function, and it came from a linear BRS transformation. And therefore, it doesn't go to 0, it remains. And then we get an information from the Slavnov-Taylor identity about this green function. And that information applies only if the screen function has on-shell lines. Yep. Good point. We, in principle, have to multiply with the inverse propagator of the original anti-ghost field, or in general terms, you would say on this level with which inverse propagators we multiply, and we would decide here in this case we multiply with q square times p square minus m square times p prime square minus m square. That is the least we should do. And then maybe in order to be even more precise for the Dirac propagators, we could also divide by p slash plus m, and here divided by p slash prime plus m. The denominator doesn't go to 0. But that is what we do. So we multiply here with a massless propagator. And actually, yeah, okay, I think that is enough. That is what we do. And then we see what happens. And then that is what we discussed in the morning. So this amputate on-shell is maybe still a little bit loosely defined. So we could now still decide for ourselves whether we, on top of this, multiply with wave functions u of p, u bar of p, or whether we do that later. But anyway, here we have an object which is not immediately an S-matrix element, but which is very, very closely related to S-matrix elements, and which can be very simply transformed into an S-matrix element by simple multiplication. Okay, so let's do it. So what happens here? What happens here, first of all, by doing this multiplication, we multiply with those inverse propagators, then this is cancelled, that is cancelled. And from the photon propagator, what happens? So with this q mu, the transverse part of the photon propagator drops out. Only the longitudinal part of the photon propagator remains, which is the one proportional to xi. And fortunately, exactly the xi drops out entirely because of the 1 over xi here. And therefore, if we then amputate the photon propagator, simply xi cancels, q square cancels, and the additional 1 over q square is amputated, and so the whole object here goes to 1. And then what remains is just this here. So minus I g gamma nu. And then let's say we multiply with speedors, so then we would get u bar of p in this case times u of p prime in the other case. Times q nu, times another q nu from here. So, and this is exactly nothing but q nu times j nu in the notation of our discussion. I think this was section 252, where we discussed the gauge independence of that process. And so there we also said that the gauge dependence drops out, because if we multiply the fermion line, which we call j nu, with the photon momentum q nu, it goes to 0. Yes. 0, yes. The q square drops out. Yeah, after we multiply with it, it drops out. Before it doesn't drop out. Q square times q square. So let's say this is really the main part from the photon propagator, I would say. So I would read it like this. This is really the essence of the photon propagator, and that will be amputated. And this is kind of the numerator of the photon propagator. And if we multiply that with q, then the transverse part drops out, and what remains is the longitudinal part, which is xi, times this. If we multiply this with q, we get q square over q square drops out, and another q remains, and the xi remains, and then we get this q nu, and the xi drops out. So this is the point. So we get from here, from this Lyapunov-Taylor identity, that, let's write it here, we get this, which is graphically this expression. If we take this fermion line on shell, including the spinos u bar and u, and contract with the incoming photon momentum, then we get 0. And so this shows you that our observation that we made in that section, and also in the last semester, where we discussed the xi independence of such processes, we derived explicitly that this relation holds from looking at the Feynman diagram, and now you see that this derivation is not an accident, but it follows from BRST invariance of the whole theory. By using on-shell's Lyapunov-Taylor identities, you discover that this is a special case of this whole general apparatus. And clearly, this identity is an all-order identity, so you can derive now, if you want, the same consequence at all orders. So, can now be generalized to higher orders. Okay, and then I would say we are almost done. Just the last thing corresponding to the exercise. And also I want to say that I stressed many times whenever we had these observations already in the last semester, I always said this follows from gauge invariance. Now you know why it follows and in what sense it follows from gauge invariance, because gauge invariance was replaced by BRST invariance. BRST invariance implies Lyapunov-Taylor identities, and this is actually a special case of Lyapunov-Taylor identities. That is the way in which it corresponds to gauge invariance. By the way, here in the linearized BRS transformations, you now see why they are relevant. They are relevant because they are the ones which do not drop out if you go on shell and amputate for S matrix elements. And these are exactly the ones from QED, right? That is essentially the ones, not from QED, but from that exercise sheet that we had already last semester, where we discussed exactly the linearized BRS transformations, and we already made the analysis of Kubo-Ojima and the QB operator and so on, and discussed the physical Hilbert space as a quotient space. So you see now that this emerges at all orders from the full Lyapunov-Taylor identities. So therefore you see that that analysis that we did at the time was not just a toy model for free theory with no interactions, but is the thing which automatically comes out of the all orders Lyapunov-Taylor identities if we look at S matrix elements. And therefore, as I already said, that analysis, which looked like a simple tree-level analysis, is actually applicable to the asymptotic theory of S matrix elements in the full field. Okay. Good. Okay, sorry, let's maybe hurry up a little bit more so that we can also do the exercises. What we have just done was an illustration of the Slavnov-Taylor identity for gauge independence. And now let us look at an example relevant for unitarity of the S matrix corresponding to the exercise sheet. So we define a matrix element M mu nu, which is the green function psi bar A mu A nu, and we amputate and go on shell. That is exactly how this mu nu was defined, except that in this case indeed we did not put the epsilon polarization vectors, but we did put the u and u bar spinos for those fields. That is how it was defined. But I do not write this in the notation. You know what we mean by it. The Feynman diagrams corresponding to it are these ones. Three level Feynman diagrams for quark antiquark going to gluon in QCD, with a triple gluon vertex, which is a non-abelian diagram, and the other ones are similar to QED Feynman diagrams. Then we also define M, which is psi bar C bar, amputated and on shell. And that corresponds just to one single Feynman diagram with ghost, anti-ghost in the final state. And this is also a purely non-abelian diagram because that vertex here has an FABC in it. So now your task was to calculate the three-level Feynman diagrams to the point where you see a certain Slavnov-Taylor identity between the two Feynman diagrams, which again looks like a miracle or an accident, but actually we will see now that it follows, like in the previous case, from a general Slavnov-Taylor identity in this amputated on-shell limit. So let's do that. The thing that you need to write down is this. So let's do exactly the BRS transformation, but one of the A's is first written as a C bar, and then we take the BRS transformation of that green function. I write down immediately the four terms. The first one is S psi bar A mu and then C bar. The second term would be minus psi S psi bar A mu C bar, then plus psi bar S A mu C bar, and plus psi bar A mu S C bar. Okay, so let's call them again 1, 2, 3 and 4. And then you now have the experience you expect in the amputated on-shell limit. The first two should go to what? They should go to 0 because they have nonlinear BRST transformations only. And okay, we might still check it maybe very briefly. So how does a Feynman diagram for this 1 or 2 look like? So a Feynman diagram for this would be, we again have this special vertex which corresponds to this BRS transformation, where we have here at the same point C and psi. And then we need a diagram with an external psi bar and an external A mu and an external C bar. How could such a Feynman diagram look like? to C. Ah. Okay, very good. Like this. Is this the only Feynman diagram? No, it's not. For example, the A could also be connected to the CC bar line, but that's all. These are the two tree-level Feynman diagrams, and then there would be higher order loop Feynman diagrams as well. Okay, but regardless, there are several Feynman diagrams, but clearly again, what happened before happens now as well. If we go on shell and amputate, then we would need to multiply with the inverse propagator for psi, which means we need here a pole in the momentum of psi. There is no pole in the momentum of psi because there is no line corresponding to psi alone. And so again, the momentum is distributed over these two lines, and therefore if we go amputate and on shell, it goes to 0 because there is no 1 over p psi square minus m square. So the first two terms in the first line, they vanish. And in the last line, we have BRST transformation of the gluon field that has a linear and a nonlinear term. And again, the nonlinear term drops out for the same reason. Maybe let's nevertheless illustrate it by a small Feynman diagram. The nonlinear term has the following structure. The nonlinear term for this is a product of ghost times A. So at one point we would have a ghost and an A. And then we would need overall a Feynman diagram with external C bar. That is easy, here C bar, and an external psi psi bar, for example like this. Then we have this Feynman diagram. And again, there is no pole corresponding to the momentum of A. Therefore, amputated on shell, it goes to 0. But there is now the diagram corresponding from the linear to the linear BRST transformation, which is as follows. Here we have now the linear BRST transformation as linear of A mu is equal to d mu c. So that means at this point there is just a ghost field coming in, only a ghost. And then that will be multiplied with the momentum of the ghost in momentum space. But it's just a ghost field coming in, and then we need an external C bar, an external psi psi bar. So how can it look like? So this is now really nothing different from having an external ghost. Here we have an external anti-ghost, here we have an external ghost, here we have an external psi psi bar. Where have you already seen something with an external ghost, anti-ghost, psi psi bar? Have you already seen such a thing? C bar, psi psi bar. Maybe here. That. Okay, that's what you wanted to say, I guess. So like this. It looks a little bit weird, but it's the same Feynman diagram. Okay, so this is our term 3. Our term 3, therefore, contains this Feynman diagram, but with a small modification, namely multiplied with the ghost momentum. That is exactly what appears in the Slavnov-Taylor identity. K mu times m. Now diagram 4. Diagram 4 is this one here, where SC bar is minus 1 over xi d mu a mu. So, long story short, this is already a linear BRST transformation, and we directly get a green function psi bar AA, which is this green function here, but 1a is multiplied with the momentum and times 1 over xi. So times 1, a is multiplied with the momentum, let's say minus 1 over xi times minus I times p into a nu. Now, what happens if you amputate and go on shell? I think we can immediately write down the result, which is now hopefully obvious. The first two terms go to 0. The third term goes to one of, you know what is the expected result. It's the one from your exercise sheet, namely m times one momentum is equal to mu nu times the other momentum. And that is exactly what we get here. Let's just check the i's and the signs and so on by looking at it. So here you get the green function with CC bar. Amputated on shell just does the obvious thing, and then we multiply with minus I times the momentum which flows from the inside into the ghost field. Here we get also exactly the expected mu nu times 1 over xi times I pa. This is the other momentum, exactly like in the Slavnov-Taylor identity that we expect, also times minus I, but also times another minus. And now something happens. If we amputate, it's a little bit complicated because the photon propagator or gluon propagator that we have to amputate is now important. It is of course matrix valued. So it contains a longitudinal part and the transverse part. And we need to amputate the entire propagator, but only the longitudinal part matters because of this. The transverse part drops out entirely. The longitudinal part matters, but the longitudinal gluon propagator is proportional to xi. If we amputate it, then the 1 over xi here drops out, and therefore we get just the amputated result without 1 over xi times the momentum, and then we get this desired relation, namely k1 mu times mu nu is equal to k2 nu times m, as in the exercise. And again, here you see that this observation that you can make from calculating explicit diagrams, and which is important for fundamental physics properties, is actually a consequence of a more general Slavnov-Taylor identity. And also here, of course, you can go on and derive the same thing at arbitrarily high orders. So, and then I can just briefly sketch the unitarity proof. Which is simply the following. You can define a QB operator acting on asymptotic states and asymptotic fields, such that the commutator of QB with a field gives the linearized BRS transformation of the field times some transformation parameter theta as before. And the BRS transformation contains only the linearized ones, and therefore this acts exactly in the same way as the QB that we looked at already before and in the exercise sheet from last year. And then using the Slavnov-Taylor identity amputated and on-shell proves the following. It simply proves that this QB commutes with the S operator. That's really the essence of all these relationships here. This is basically the same statement or the specialized statement of the general fact that this QB commutes with the S operator. And then we know this QB is Lorentz invariant. The original S operator is Lorentz invariant, and so then you can define the physical Hilbert space as the quotient space. And because of the commutation relation that S commutes with QB, you can say that S restricted onto the physical Hilbert space is well defined, first of all. So if you are in one equivalence class, you are mapped into one unambiguous equivalence class, so the equivalence structure is retained and it is unitary. Again, because of the commutation relation. And that's it. Then in this way you can prove the unitarity of the S matrix, and you just have to fill in some details which basically work similarly to this, just generalized. And that, my friends, ends our discussion of quantized Young-Mills series. Let me just give you the reference where this is done exactly in this way, is Kuko Ojima. But already all the other people that I mentioned in the morning, Toft, Zinchester, BRST, they all also did unitarity proofs. They did not yet use exactly this language, but they did equivalent manipulations. But this is probably the most elegant formulation of the unitarity proof, where you see an elegant structure emerging from the Slavnov-Taylor identities. Okay, what I didn't discuss now is the gauge independence of the S matrix, such that the Xi parameter also drops out. That is a little bit different, so you need to extend, or in the most elegant approach, you extend the Slavnov-Taylor identity such that the Slavnov-Taylor identity also tells you what is the Xi dependence of various quantities. But let us not discuss it in detail, you can find it in the references, but the basic logic is now always the same. Slavnov-Taylor identities go on-shell amputate in order to extract physical information, and the off-shell Slavnov-Taylor identities are important for renormalization. Very good. That is the structure, and the physics of the theories and of the BRST formalism is now really contained in the linearized form, which is very simple, and as I said, this will change in an interesting way if we go to the electroweak theory. But also there, then historically, it was of course very important to prove those properties of unitarity. There it was maybe even more important because it was even less obvious, and you might know that you need the Higgs boson to make the theory unitary and so on. So that was a big discussion also historically, but one can prove it using identical methods. All right, then the chapter is done and we can close the lecture and come to the exercise.